Hello everyone, and welcome to today's presentation on digital data transmission techniques. In today's digital world, data transmission plays a crucial role in communication. So digital data transmission techniques enables us to transmit data efficiently and reliably over various communication channels. So I will define a digital data transmission first, but if you want to know more about this topic, you can go to refer to our previous lectures. So digital data transmission refers to the process of transmitting digital data from one device to another through a communicational channel. So this process involves converting digital data into signal that can be transmitted over a communication channel. So we have synchronous transmission and asynchronous. And I will first explain asynchronous transmission. And we are talking of asynchronous transmission. This is a digital data transmission technique where data is transmitted one byte at a time, right? In asynchronous transmission, the transmitter and the receiver are not synchronized, and the data is transmitted at irregular intervals. So this technique is used in low-speed data transmission applications such as keyboard units or serial ports. And here we're talking that no clock signal is required. Of synchronous transmission, we are talking of a digital data transmission technique where data is transmitted in synchronized blocks or frames. So in synchronous transmission, the transmitter and receiver are synchronized using a clock signal as compared to asynchronous. We are saying there are no clock signal in asynchronous, and in synchronous we are saying that there is a clock signal, right? So this technique is used in higher speed data transmission application as compared to asynchronous, where we are talking of low speed data transmission. So this technique is used in higher speed data transmission applications such as fiber optic communication. Then we move on to errors, detection and correction. We need to define an error. What is an error? So when you're talking of errors in data transmission, occurs when the transmitted data is corrupted or altered during transmission. So these errors can occur due to various factors such as noise, interference, and hardware faults. So when there is an imperfect medium or environment exists in the transmission, is prone to errors in the original data. And we have three types of errors that I mentioned in this presentation. There is a single bit error and multiple bit error, burst error. So when you're talking of single bit errors, single bit error occurs when a single bit of data is corrupted or altered during transmission, right? A single bit is corrupted or altered during transmission. And when you're looking at our diagram here, we see that there is one digit that is corrupted, one bit value, which is a 1 from the original data. The second one that is corrupted to 0. So the original data is different from the received data. There is 0 1 and here there is 0 0, and we are saying that a single bit of data is corrupted. All right, so I can also give an example where 101 is transmitted and the receiver receives a 111, 101, and then the received bits are 111, and you can see that there is a single bit error that is occurred. Then on multiple bit errors, we are saying that a multiple bit error occurs when multiple bits of data are corrupted or altered during transmission. For example, if the binary data given here, that's 0100 110111, then you can see that a 1 changed to a 0, a 0 changed to a 1, and a 1 changed to a 0. So you can see that the 3 bits changed, right? And you can see that 2 or more bits in a transmission can change, right? So the original data is different from the received data, and there are multiple bits of the binary value changed, right? We can see that you can see that a 1000 1000 1000. So we cannot say 100, but we can say 1000 is transmitted and the receiver receives a 1101, right? So there are multiple bit error has occurred. Then we are talking of best errors. We are saying that a best error occurs when a sequence of bits is corrupted or altered during transmission. This one is different from multiple bit errors because we are saying that there is a sequence of bits that is corrupted or altered during transmission. We can see here the message that was sent is 10110011. There is a sequence of bits that changed. 011 changed to 100. This is what we call a best error, and you can see the difference with multiple bits error. So we move on to error detection. And error detection is the process of detecting errors that occur during data transmission. There are several error detection methods, but I mentioned parity checks, then cyclic redundancy check, then checksum, and I'm going to explain them in our following. So here are the detection methods that I'm going to explain. So when I'm talking of parity checks, we are talking of parity checks involve adding a parity bit to the transmitted data. The parity bit is calculated based on the number of ones in the data. If the receiver receives a data block with an incorrect parity bit, an error is detected, right? For example, if even parity is used and several ones is even, then one bit with the value 0 is added. This way, number of ones remains even. If the number of ones is odd, to make it even, a bit with the value 1 is added. So the receiver simply counts the number of ones in a frame. If the count of ones is even and the even parity is used, so the frame is considered to be not corrupted and is accepted. If the count of ones is odd and odd parity is used, the frame is not corrupted. If a single bit flips is in transit, the receiver can detect it by counting the number of ones. But when more than one bit is erroneous, then it is very hard for the receiver to detect the error. That's what we call. And there is two-dimensional parity. And we're talking of two-dimensional parity. This involves adding parity bits to both the rows and columns of a data block. This method can detect and correct single bit errors, right? So here this is an example that I'm going to use. So here's the example that we are going to use. And in this method, a block of bits is organized in a table. So here the original data is given. There is 0, 1, 1, 0, 1, 1, 0, right? You can see that there are 7 bits, 2, 4, 6, 7 bits in 4 blocks. So here we need to organize our information, our bits into blocks, right? So the first block is given, the second block, the third block, and then the fourth block is given. So after that, we calculate the parity bit for each data unit, so that we write the row parity and then the column parity. And to find the row parities, we use the matrix, right? So to calculate the row parities, you need to calculate the parity of each row. So the parity of a row is calculated by counting the number of ones. So in our first row, right, we see that there is 0, 1, 1, 0, 1, 1, 0. So you need to calculate the parity of each row. So the parity of it is calculated by counting the number of ones. And here we see that there are 4 ones in our row, right? So if the count is even, the parity is 0. So we have 4 ones. So our parity is 0. We move to the next row. We see that there are 1, 2, 3, 4. So our parity is even. Our number of ones is even. So the parity is also 0. Then on the third block, we see that we have 1, 2, 3, 4, 5. We have 5 number of ones. And if the count is odd, which is 5, the parity is 1, then we put a 1 here. And on the fourth block, we see that we have 3 ones, and the count is odd, so the parity is also 1, right? So we also move on to the column parities. To call the column parities, you also need to calculate the parity of each column. So the parity of a column is calculated by the number of ones in the column. If the count is even, the parity is 0. If the count is odd, then the parity is 1. So now column, the first column we have 0, 1, 1, 0. So there are two count of ones and the count is even, so our parity is 0. You continue to do that. On the second row we have 3 ones and this is an even, and you see that the parity is 1. On the third column we have 2, which means that this is even and the count is even and our parity is 0. The fourth one, there are 2 zeros, the count is even and our parity is 0. Then we look on the fifth column, we have 2 ones and this is even, our parity is 0. On the sixth column, we see that we have 3 ones and then we see that this is an even, an odd count and our parity is 1. We also look at this at the other column. We see the last column, the seventh column. We see also that there are 2 ones and the count is even, so our parity is 0. This is how we calculate our parities. And then moving on, I said that the first step we calculate the parity bit for each data unit. Then we organize them into a table like what you are seeing. We then calculate the parity bit for each column and create a new row of 8 bits. You see that we have 8 columns now. Then, considering this example, we have 4 data units to send. They are organized in tabular form. So we then calculate the parity bit for each column and create a new row of 8 bits like what we did. Note that the first parity bit in the first row is calculated based on all first bits. So the second parity bit is calculated based on all second bits and so on. So we then attach the 8 parity bits to the original data and send them to the receiver. So the 2-dimensional parity check increases the likelihood of detecting best errors. So a best error is more than n bits is also detected by this method with a very high probability. We need to look at cyclic redundancy check. Cyclic redundancy check. This is another way of detecting error, and we are talking of cyclic redundancy check. This involves calculating a checksum based on the transmitted data. So the checksum is appended to the data block. If the receiver receives a data block with an incorrect checksum, an error is detected. So this technique involves binary division over the data bits being sent. So the device is generated using polynomials and the sender performs a division operation on the bits being sent and calculates the remainder. This is grade 3 mathematics. So before sending the actual bits, the sender adds the remainder at the end of the actual bits. So the actual bit, data bits plus the remainder is called a code word. So the sender transmits data bits as code words. So the receiver performs division operation on code words using the same CRC divisor. So if the remainder contains all zeros, the data bits are accepted. Otherwise, it is considered as there is some data correction that occurred. This is cyclic redundancy check, this division, grade 3 division, grade 3 method. So another one is the checksum. And checksum involves calculating a sum of the transmitted data. The checksum is appended to the data block. If the receiver receives a data block with an incorrect checksum, an error is detected. We will move on to error correction techniques. So here error detection techniques involves using algorithms to detect errors in the transmitted data. So there are several error detection techniques, including Hamming codes, and this involves adding redundant bits to the transmitted data. The redundant bits are calculated based on the data bits. If an error occurs during transmission, the receiver can detect and correct the error using the redundant bits. Then we have the Reed-Solomon code. This one involves adding redundant bits to the transmitted data. The redundant bits are calculated based on the data bits. If an error occurs during transmission, the receiver can detect and correct the error using the redundant bits. Right. Then we can talk of automated repeat request, ARQ. Involves transmitting data blocks with error detection codes. Right. If the receiver detects an error, it sends a request to the transmitter to retransmit the data block. So return sends data when errors are detected. We need to move forward to data link control protocols, and these are protocols that are used to manage the transmission of data frames between devices. There are several data link control protocols, and they are given on the screen. We have HDLC. This is the high level data link control, and this is a protocol that is used in WANs, the wide area networks. It provides error-free transmission of data frames between devices. These are bit-oriented protocol for point-to-point and multi-point links. Then we can talk of point-to-point protocols. There's the triple P. This is a data link control protocol used in point-to-point connections. It provides error-free transmission of data frames between devices. They're used for direct connections such as dial-up. We have a serial line internet protocol, and this one is a data link control protocol used in serial line connections. It provides error-free transmission of data frames between devices. This is a protocol for IP. Thank you for your attention, and I welcome any questions in the comment section. Thank you.